simulations.
All right. Hi, everyone. So my name is Vio. I'm a postdoc at ULB in Brussels. And yeah, I'm happy to be here to present you these new historically calibrated projections of the Antarctic ice sheet that were produced with the precious help of my co-authors that I'd like to acknowledge in the framework of the project Protect. Okay, so to set the context a bit, we know from observations, as we've heard again this morning, that the Antarctic ice sheet has been losing mass over the past decades. This essentially in West Antarctica, and more specifically in areas that were subject to a thinning and hence a weakening of the buttressing ice shelves due to an increase in subshelf melting. But nevertheless, the future evolution of the Antarctic ice sheet remains unclear. And one of the reasons for this uncertainty is that under a warming climate, we may expect, on the one hand, a further increase in this subshelf melt, and on the other hand, an increase also in snow accumulation and surface runoff, which both mitigate each other and contribute to the ice sheet surface mass balance. And so in this context, our goal here is to try to investigate what will be the balance between these competing processes in the future, and hence how it will influence the evolution of the Antarctic ice sheets. And so to investigate this, we use the ice sheet model CORI that Frank presented earlier. We use it at a 16 kilometer spatial resolution. And with it, we run an ensemble of simulations that covers uncertainties in both ice-ocean and ice-atmosphere interactions. So we begin our simulations in year 1950 with hindcast until 2015, and then we apply climate projections from 4 CMIP6 climate models, which are listed up there, and that have projections available under both SSP 126 and SSP 585 until 2300. And so after 2300, we no longer have projections available, and so we keep our climate forcing constant in time until the end of the millennium. So overall, we have defined an ensemble of 100 simulations using a Latin hypercube sampling over the parameter space, which is summarized in this table here, and which covers uncertainties in, for example, the atmospheric lapse rate, which influences the melt elevation feedback, in some parameters from our positive degree day scheme, which influences the amount of surface melt and runoff. We also use a panel of subshelf melt parameterizations, and for each of these we cover uncertainty in a parameter which modulates really the sensitivity of the subshelf melt to the ocean thermal forcing. Okay, so this is a very brief overview of our experimental setup, and now we can have a look at how this ensemble of 100 simulations behaves over our historical simulation. And so this figure shows the evolution of our ice sheet mass balance and its main components between 1950 and 2015, and compares it with some observational estimates, the red boxes on the figure, which they come essentially from satellite-based studies. And so what we can see is that our ensemble of 100 simulations produces a quite large spread of mass change over the past decades, really due to the uncertainties that it accounts for. And so therefore, what we do as a next step is that we calibrate our ensemble by applying a Bayesian framework, which means that we attribute a higher weight within the ensemble to simulations that better reproduce some estimates of the regional mass balance over the past decades, listed on the table here, and that come from the latest IMBY assessment. And here you see that when doing so, it allows to reduce quite significantly the spread in our projections, and that we now have a calibrated ensemble which reproduces the historical trend in relatively good agreement with the observations. And this also when we have a look at the spatial pattern of mass loss over the past decades. Okay, so now that we have calibrated our ensemble and validated its behavior over the past decades, we can now have a look at the behavior, the evolution of these calibrated projections until the end of the millennium. And so this behavior is summarized with these figures here, where you have on the top the evolution of the distribution of our sea level contribution under our 2 emission scenarios. And on the bottom, we have a figure very similar to one that Hélène presented, where we have at different times throughout the millennium, the probability of having a retreat of the grounding line within the ensemble at a given location. So the redder the color, the more the simulations from our ensemble agree on a retreat of the grounding line at a specific location. Okay, so what can we see? So if we focus first on the 21st century, we see that there is no strong influence of our emission scenarios on our projected mass loss. And that we have in both cases mass loss which is projected to remain essentially confined to the Amundsen Sea embayment, like Thwaites Glacier, leading to a very similar distribution of our sea level contribution, with in both cases, under both scenarios, a median contribution to sea level by 2100 of about 5 centimeters. But however, the projection starts to diverge quite a lot after the end of the century for our two emission scenarios. And so we see that under SSP 126, mass loss is projected to remain essentially in West Antarctica, and more likely we see, this is redder, in the Amundsen Sea embayment, and this even on the long term. But in contrast, under SSP 585, we project a quite significant acceleration in ice loss after the end of the century, which is associated with, on the one hand, a complete collapse of the West Antarctic ice sheet that we see here. And we see that we expect it to be completed between around the year 2300 and 2500. And on the other hand, we also have some long-term grounding line retreat in the marine basins of East Antarctica. And so altogether, this leads under SSP 585, so this high warming scenario, to a median contribution to sea level rise of about 7 meters by the end of the millennium. So now to better understand the drivers of this projected ice loss, here we have a look at the evolution of our main mass balance components over the next centuries. And so if we again focus first on the shorter term, we see that the projected ice loss in the Amundsen Sea embayment during this century is driven very similarly to what is currently observed by an increase in subshell melting, which is shown in red in these figures. And we see that while under SSP 126, this subshelf melt is expected to stabilize as of about 2050, so the second half of this century. This is not the case at all under SSP 585, where we have this subshelf melt which keeps increasing during this century and after it. And so still under this SSP 585 scenario, we see that on top of this increase in subshelf melts, our projected acceleration in ice loss after the end of the century coincides with a decrease in our ice sheet surface mass balance, which is shown in blue in these figures. And so here, if we have a closer look at the evolution of our main surface mass balance components, we see that this decrease in surface mass balance is in fact triggered by a quite significant increase in surface runoff, shown in yellow, and which is expected to outweigh the increase in snow accumulations, shown in light blue. And so now to better understand the evolution of our Antarctic surface mass balance under a warming climate, and also to become more independent of our emission scenario, here what we do is that we relate our median surface mass balance fluxes over both the grounded ice sheet and the ice shelves with the regional atmospheric warming around Antarctica. And when we do this, we see first that over the ice shelf, the threshold at which the surface mass balance starts to decrease occurs already at around 2.5 degrees of warming. And in contrast, over the grounded ice sheet, the surface mass balance keeps increasing due to this increase in snow accumulation until around a regional warming of around 7.5 degrees. And so hence, since it increases, it's mitigating our ice loss. And then above this 7.5 degree threshold, the surface mass balance starts to decrease along with its sea level mitigating potential, which kind of means that then our atmosphere would shift from a mitigating to an amplifying contributor of Antarctic ice loss. And so we've seen the slides before that such a threshold of 7.5 degrees could already be reached by the end of the century under this SSP 585 scenario. Okay, so I think I'm going to leave you with these summary points here, and I just quickly would like to add that everything that I've just presented is part of a study which is currently under review in the cryosphere, which means that the preprint is available if you would like to go and check our other results and more details, or just come and find me. And yeah, thank you very much for your attention. I'm happy to take any questions.
Thanks, Vio. We've got time for just one quick question. No? All right, well, we'll move on to the next speaker then. Thanks again. Next up, we've got our second